the number one misunderstood concept in chemistry. This is the number one thing most forgotten by chemists, because chemists and historians don't always get along. For some reason they forget about, well, the people involved. Or the person who loves history forgets about the chemistry behind it. So we're going to talk about origins of modern atomic theory. So to do that today, the first thing to look at is this quote here. It states that scientists are not dependent on the ideas of a single man, but on the combined wisdom of thousands of men, all thinking of the same problem and each doing his little bit to add to the great structure of knowledge which is gradually being erected. This is from Ernest Rutherford. So, we are going to do the work of many men and women right now. Okay, to do this, I am going to ask you to answer a single question. Your job is to figure out what is the configuration or design inside of this closed container. Each of you will receive a closed container like this one here. Your job is to figure out what is the design inside of this container. To do this, the things you know is, first of all, inside of this container there is a steel ball. Okay? That steel ball is inside of it. That's not what you're trying to figure out. There is a steel ball in there. First of all, an example of what you don't want to do. If you have a friend and you don't want them to say, don't look at me. No, that's all we want to do is look at you. Or don't imagine me as a gorilla. You know? I mean, you can't not do it. But it's very difficult. Now, the frustration you felt in this activity, this idea here, this observation is a model. You made a hypothesis, which was a guess. This is exactly the same thing that we do in science. We make a guess. We're like, I think it's this. You should have made that guess really quick. It's hard to do, especially if you want to be right. Right? You're like, I can't draw it yet. I don't know if it's right. The uncertainty is overwhelming. It is so hard to draw that within 10 seconds. Many of you didn't. You couldn't do it. You're like, oh. That was 10 seconds for me. Come on. I counted to a minute. No, I mean, 10 seconds. Anyways, it's very difficult to do. And then after you get your result, you're like, oh, wait, what'd you get? What'd you get? Hey, what'd you get? You want to know. You want to know if you're right, right? Because if she got it, you know it's right. You know? She always is right. But now, everybody goes through that. I went through this. First time I did this. And then I handed my thing back in, and I'm like, man, maybe if I just sneak in there and the teacher's not looking, I can look at it. Wouldn't it be nice if I told you what the shape was really in there?
You're not going to tell us?
Yeah. This here is a model of an atom. And the model of the atom is just like this. You cannot even see the outside of it. Wow. You can't even see the outside of it. And the inside of it is as difficult, or actually much more difficult, to predict than this is. And guess what? Even if you think you have the right answer, you can't look inside.
That must be so frustrating.
Very frustrating. Very frustrating. Now you have to be up for the challenge of trying to look at evidence and see, this is a model of a piece of plastic. You were trying to determine it by not looking at it. This is called indirect observation. Atoms, the only way we know they exist is indirect observation. So we're going to look at, well, how did they come up with a model of this? Even if they were frustrated, what did they do? Why did it take so long in history for us to even come up with an idea of what an atom is? Now, how many of you have ever made a model before? Okay, what'd you make a model of?
Failed buckyball.
Failed buckyball, yeah. A cell, all right? Now, take the cell example. Was the cell a real cell?
Yes.
Was the model of the cell you made a real cell?
No.
No. What was wrong with it? One, it was too big. Second of all, if it was small enough, would it actually function as a cell if you put it in your body?
Probably not.
No. I mean, if it was a plant cell, it would be even worse. But you made it out of a piece of plastic or cotton or all sorts of cool things. Your cell might have been the best cell in the world. Or your model airplane might have been the best model airplane in the world. However, could you hop inside of it and fly to France? It'd be really cool, you know, if you can figure a way around that. But a model is interesting. A model is not the real thing, no matter how good the model is. No matter how good the model is. The funny thing about models, which we're going to see today, is models are 100% wrong. 100% wrong. So if you're like, I'm wrong, guess what? You just made a model. I'm wrong. Now, the interesting thing about models is the model that is accepted by most people is considered the right one. It's still wrong, 100% wrong. So if you're like, the model of the cell, I made a model of the cell, guess what? You're 100% wrong, but yours might have been the rightest one of all. Yeah, really annoying. You're like, wait a minute, I know my model's the best. Mine should be right. Well, it's just right if everybody else agrees it's right. So your pictures you drew, okay, people in another country drew these pictures. Are they right? Are you right? What's up?
I'm right.
Yeah, of course you're right. So let's see if you're really right. The cool thing about this activity is this is not an atom. We could actually open them up, but I'm not going to.
Wow, that's even worse. That's like saying,
We cannot open these up. They're plastic, but we can't open them up. All right, those people over there, yeah.
Why can't we open it up?
Can't open them.
Why?
But we can look at the pictures. So, number one, which one's number one? Which one? Top, bottom, second row, third row. Where's number one? Who had number one? Anyone had number one?
Number one is
This one?
no.
That one?
No, wait, the first one you pointed at. Yeah, that one.
That one? Number one is that one.
No.
All right, let's see. Number one. Oh, number one is this one. Apparently, according to other people's observations. Number two, which one?
Either the second one or the fourth one.
Second or fourth, here or there?
No, the fourth one from the left. I think it's the second one. Like, second one on the first column.
This one?
No, second one on the first row.
This one?
It's either that or that.
All right, let's see. Two. That one right there.
That's a lie.
Hey, I'm just reporting what they told me. All right, number three.
That one.
Oh, three is this one. All right, number four. Which one's four? Top one. Number five. Here we go, number five. Oh, soccer goal, number five. Number six.
The triangle.
Triangle. Oh, close. Number six. Number seven. Oh, wait, no, number eight. Sorry, number eight, triangle. Number nine. Got number 10.
What's 7?
Number 11. Bottom. Very good. Number 12. Circle. Yay. And number 7.
The line.
I don't know which one it could be.
The line.
All right, D-line. So, yeah, the cool thing about this is you will not be graded on your drawings, but I want you to know that science can be frustrating. We're going to talk about what evidence we have for the model of the atom currently. So the first thing is the scientific method is used. This is what you just used. The first thing we do is to come up with a hypothesis. This is a tentative explanation for an observation. It can be really fast. It can be really slow. Okay, sky's blue, hypothesis, because sunlight bounced off the water's blue. That's the hypothesis. Then, what you would have to do is you could test that by experiment. Okay? So you get a light source and you get water. And you see if the reflection causes a blue coloration. You might have to get a very, very large model to do this. But you got to test it by experiment for a hypothesis. So we looked at this, wrote a hypothesis down, then now we can test it out. You retested it. Experiments. Test to look for observable predictions of a hypothesis or theory. It either proves your experiment correct or incorrect. Either way, it's a win. You got evidence one way or the other. It's okay if your hypothesis is wrong. Then once you have these experiments lined up, if you have enough experiments, you can have laws that are brief statements that summarize past observations and predict future ones. So it's being able to predict the future. That's what a law will help you predict in science. Right? And theories. One step up from laws, they are unifying explanation. They try to unify a set of observations, facts, and laws into one unified theory. And this theory requires all of these things to be in agreement with it, or as much as possible. Laws are something that always tend to happen and are predictable. Although they could, a law could be broken. It's not a fact. It's called a scientific fact because it's something that's completely observable over and over and over and over and over and over and over again. However, theories are just unifying a bunch of things together. That does not mean that a theory is truth. A theory is just still an idea that has evidence supporting it. Some theories, a lot of people disagree on them because it's trying to unify laws, which are there, facts, well, scientific facts are just things that are reproducible, and observations, things you see. If some person sees it's blue and the other person sees it's blue-green, okay, they've got different observations, right? Okay, they can have arguments about those and talk about them for a long time. One person says, no, I think it's a little circle in the middle. They say, no, I think the circle's a little bit bigger. Those disputes don't necessarily mean one person is right or wrong. They both are trying to make a model of reality. And the theory is trying to unify these sets of observations. The problem with a theory is, if you got one observation or fact you think is a fact, but it's really not, it's proven wrong, what happens to your theory? It starts to have some problems, got some holes in your theory. Doesn't mean it's all wrong, maybe it's just the right idea, but you said something here that didn't agree with this. So, the scientific method, as you may be aware of, you make an observation. You gather facts, which are called scientific facts. They're not really true-false facts. They're based on observations, so they're things that are not disputable. For example, if you mention the color of this, you said it was a reddish color. Boom, that would be indisputable. Everyone would agree upon that. Yeah, and you could say it's every single color but red is being absorbed. Everybody could agree upon that too. But if you went a step further and said, I think those are magnets. That's called an inference. It might be debatable. Some people might say, well, they look like magnets, but maybe it's just a piece of cardboard stuck together with glue. So you've got to be aware of it. The observations support the scientific facts. You need to propose a hypothesis, making a guess, a tentative explanation, also called a guess. Test the hypothesis, performing an experiment. Gather more facts and generate new hypotheses. Happens all the time. New hypothesis, new hypothesis, new hypothesis, new idea. Test it out. Retest a new hypothesis. Show that the results are reproducible. Has to be reproducible for it to be scientific. If you did it once and you can't do it again, guess what? You're like these here. These elements here, they discovered them and then they said, wait, nobody else could reproduce it. Someone discovers it, nobody else can reproduce it. Is it really there? There's a lot of debate there, and most of it goes upon, can you reproduce it? Can you reproduce the experiment? Propose a theory. The theory comes up, and that theory helps to explain how nature operates. Explains as best we can our observations. It's derived from observations, so it's all about observations that are made. It simplifies them and categorizes the information to try to simplify what you're seeing as best possible. The models we create, though, are 100% wrong. We know that. So we're trying to simplify it as best we can to predict what's going to happen and explain why something happens. A model must be sensible, but it has limitations. Okay? It must make sense, but it is limited in many different ways. Okay? The model that you make of a cell, for example, maybe not everything is to size, or not everything operates the same way. Or there are limitations based on the fluidity of the model. Maybe the model is supposed to be something that's very flexible and moves very easily. Or it's something that can move and your model can't move. Or the size is different. Or the three-dimensionality is different. Or there's many, many limitations you could have on any model. Now, properties of a model, first of all, they are human invention. We did a drawing, that's a model. Three-dimensional drawings or three-dimensional models are the same thing. They're just in three dimensionals. Computer, doesn't matter if computer does it or if you do it, it's still going to be a human invention. It's not just a blown-up picture of nature. If you really took a picture of a cell and you were able to do that, it would not look exactly the same as your model. Not going to look the same. Your model might have more colors and so on and so forth. Models can be wrong because they are based on speculations and oversimplification. Okay, models can be proven incorrect and thrown out. And then you just got to take the data you have and make a new model. And then you get more data, you make a new model. Make more data, make a new model. And you go loop to loop to loop to loop to loop. And if you're lucky and your model is accepted by a lot of people, your name gets known around the world. If not, nope, it just gets thrown away and we keep going through the process. They become more complicated with age. So as the model, as people add more things to the model, and they say, well, if this model works, then we're going to add this to it. It gets more complicated trying to explain the model. You must understand the assumptions in the model and look for weaknesses. If you don't know what's being assumed in the model, then you may not be able to see what it's testing and what it's not testing. Some models cannot show everything, obviously. Now, we learn more when the model is wrong than when it is right. Okay, wrong meaning when there's something that is provable against the model, we learn more through that process. If it's just right and accepted, we don't tend to learn as much as long as it's still accepted. For example, we know that the sun goes around the earth every day. We can see it. It rises in the east and sets in the west, right? So our observations prove that the sun goes around the earth. If we accepted those observations, okay, would we have been able to go to the moon? Yeah. Could have been some problems. So the observations that are accepted sometimes can be completely wrong and accepted for a long time and everybody could be happy with it. Okay? For example, some of you still accept that the sky is blue because the sunlight bounces off the surface of the ocean and it makes it blue. And guess what? Guess what? I'm not saying your model is completely wrong, but the evidence proves otherwise. Now, you would have to gather lots of evidence to prove it to yourself. Those are called preconceived notions. Everybody has them. You got an idea of what is right, and it's stuck in your head. And until you knock that out, whatever it is, and draw something new, you're going to still believe that. Doesn't matter who tells you what. Doesn't matter if I tell you that this is the way it works, or if it works differently. You have to see evidence of that. And no matter what scientists we have, everybody has those ideas somewhere in their head, and they have to work through them together. All models are wrong. What? Yeah. All models are wrong. The best model is the one that is accepted. It's called the best model. It's still wrong. Still 100% wrong. You're like, wait, I just made a model of a buffalo. Well, it's still 100% wrong. Even if you make it perfect and you use 60 carbon, it's still wrong. So, these are the properties of a model. Laws. These are some examples of laws that we use oftentimes in chemistry. Conservation of mass. That's the first one. Okay, mass cannot be created or destroyed in a chemical reaction. Law of definite proportion. Compounds have a constant composition by mass. So that is where we get our percent composition. They react in specific ratios by mass. And this is Dalton's presupposition that the amount of hydrogen to the amount of carbon, or the amount of hydrogen to oxygen come together to make water, is a specific ratio by mass. And this ratio here, the way they come together, relates us back into the mole ratio in stoichiometry. Multiple proportions. When two elements form more than one compound, the ratio of masses of the second element that combine with 1 gram of the first can be reduced to small whole numbers. So this is the mole ratio idea. This was called the law of multiple proportions. So we have a few laws that are already in place about masses of substances. And all of this was things we measured when we looked at stoichiometry, the masses and the moles of substances. This is an example of the law of multiple proportions. Mercury has 2 oxides. One is 96.2% mercury by mass. The other is 92.6% mercury by mass. To show that these compounds follow the law of multiple proportion, we could speculate on the formula of the 2 oxides. So the formula, if we look at this, these 2 mercury oxides, the oxygen, again, and the mercury by mass is going to be a percentage. We could use this data to determine the formula of these 2 oxides by the fact that one has 96.2% and one has 92.6%. How would we determine the formula of these 2 oxides? How would we go about doing this? Without doing it, just speak through it. How would we do this? How do you find the formula of giving this information? Okay, what do we have to convert the percentage to? Okay, grams. So we assume that it's grams. Okay, and then what can we do? Okay, and we got to figure out the molar mass. But these two are both, again, two different oxides. So one's 96.2%, one's 92.6%. How would we go about that? We got two percentages of the two oxides. So, the 96.2% mercury by mass, the other percent is due to what? Oxygen. And so once we have that percentage from 100, we could get the grams, then the moles, and then set the mole ratios up so we could determine the formulas. So this is the law of multiple proportion. This is how we used it in the past. We've already done this. So here's a quote from Democritus that says, "Nothing exists except atoms and empty space. Everything else is opinion." Democritus was a philosopher at the time of Aristotle. He debated, him and his student, debated with Aristotle, and Aristotle won. That's why this idea here was unknown for a very long time. People didn't accept it. It was just an idea, just a thought, which is what philosophers do. Not a scientific fact, but he was the first to name the atom. Now, Democritus was around 460 BC in Greece, and Leucippus, 5th century BC in Greece, both believed, similarly, that the natural world consists of two fundamental principles. The first is that there are indivisible bodies called atomos. The second, there is a void, or empty space. This idea, again, was not agreed upon by the masses, and so it was forgotten about by most people in the thought-provoking world, because Aristotle disagreed. The idea that elements, that atoms were made up of indivisible bodies, things that couldn't be separated, and empty space was not an acceptable view. However, the word atomos means not cuttable. So that means indivisible, not able to separate out. They also believed that indestructible and immutable means you could not destroy an atom, you could not change an atom. There were an infinite variety of forms. So there were all sorts of these indivisible bodies. There was an infinite number. They didn't know how many there were. They couldn't test this out. And they moved through void. They moved through empty space constantly. They connect together to form clusters, was this atomism theory. And clusters give rise to substances. So if you have a cluster of certain atomos, indivisible bodies moving through a void, they give us these substances. It wasn't until much later that John Dalton was quoted to say, "Matter, though divisible in an extreme degree, is nevertheless not infinitely divisible. That is, there must be some point beyond which we cannot go in the division of matter." I have chosen the word atom to signify these ultimate particles. John Dalton, years later, decided, you know what? There might be something about these atoms. Dalton's atomic theory was in his life was in 1766 to 1844. So this was almost 1,800 years later, okay? More than 1,800 years later, he was the first one to actually come up with another idea about the atom. That was not just an idea, but it was a theory. His first postulate was that elements are made up of atoms. Atoms of each element are identical. Atoms of elements are different, are differentiated by weight. So the weight determines the different elements. Compounds are formed when atoms combine. Each compound has a specific number and kinds of atom. And chemical reactions are rearrangement of atoms. Atoms are not created or destroyed in chemical reactions. His model is called the spherical model or the billiard ball model if you play pool. Atoms are solid spheres. Means they have nothing in the inside or nothing that everything is completely solid in that spherical shape. So he believed that these objects would move and collide with other objects, and when atoms combine together, each compound is a specific number and kinds of atoms. Okay? Do we use this theory when we talk about chemical formulas? Absolutely. Okay? Absolutely. Any of the formulas we've looked at have all been specific ratios. So Dalton's atomic theory, although it has some holes, is a very clear theory of why the chemistry we see happens. And his theory was not just an idea, but it was based on experimental evidence. He actually measured these things in order to get his theory. So he had to do experiments. The philosophers did not do any experiments, so they didn't have any scientific evidence, any scientific facts. They just had ideas. The first element symbols here that were drawn up here included lime and soda, sulfur, oxygen, carbon, hydrogen, strontium, iron, zinc, copper, lead, silver, gold. Wait a minute, that's a lot of metals. Those were known about much, much earlier than the atomic theory. Those were used much earlier than even the atomic theory. Okay? Platinum, also called platinum, mercury. And the first model showed how these come together in specific ratios. So they used little pictures representing these different elements and how they would come together to form these compounds. So obviously hydrogen and oxygen, one hydrogen to one oxygen makes water. What? I know, the first one you see, you're like, wait a minute, that's totally wrong. That was wrong. That's because his evidence showed that hydrogen and oxygen came together. He didn't realize it was a 2-to-1 ratio because he assumed the mass of hydrogen was double what it really was. So he assumed it was a double mass. So he didn't know it was an H2. He wasn't able to determine that from his multiple proportions. But you're like, oh man, he messed up. He's totally wrong. Guess what? He was the first. So yeah, he's going to be wrong in some areas, right? Just like every other model. But the cool thing is, he was able to show, binary, ternary, quaternary, quintenary, and septenary. Sextenary means it was made up of 6. So all of those words here, binary compounds, ternary compounds, those are things just made of more than 2 different things. So this is really cool. First original representation of the elements. So in 1803, he came up with the spherical model. And next along came a dreamer from Russia. I saw in a dream a table where all the elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Dmitri Mendeleev in 1869. Now, that's what he wrote down in 1869. Dmitri Mendeleev was in a very large family. He was in a family of 17 children. His father died when he was 13 years old. Yes, sir? No. Should be D-I-N. Sorry about that. No, it is Russian. He grew up in, sorry about that. He grew up in Russia. He was in a family of 17 children, and his father died when he was 13 years old. Needless to say, in that day, in the 1800s, it was very difficult for a woman to get a job, especially in Russia. His mom did everything he could to raise the children, and he was one of the smartest children in his town. He applied to university, and he was immediately denied because he was too low on the socioeconomic status. He was too low. His family was not respected enough. He didn't have a father, obviously, so something must be wrong with him. So they did not allow him to go to St. Petersburg, where he wanted to go to study mathematics. So he had to go to his second choice, and he worked for years and years. And when he first wrote this down, it took him about 20 years before he actually published the table he envisioned. The first people he showed this to laughed at him. They laughed at him. They said, "Okay, Dimitri, you've had too much. Really, you got to be kidding me. You saw it in a dream." Okay, yeah, sure you did. Now, yeah, you're like, it is definitely not normal. It is unbelievable that he actually did see it in a dream, and that's his story. So, in Mendeleev's dream, he arranged the 63 known elements into a table from this dream. Now, he had been studying it for a long time. It wasn't as if it was something that he'd never looked at before. He'd been trying to work on arranging these elements. He put them in columns by similar properties. He arranged them by increasing weights. The magnitude of the weight determined the element's properties. So they are arranged by properties in columns and by increasing weight by elemental properties. It was independently developed by a German, Lothar Meyer, and it successfully predicted properties of missing elements. One of the prime examples of this was Mendeleev's table had blanks in it. There were literally blanks, and he said there's going to be something right there that will have these properties. One of the blanks he predicted was an element known as germanium. He predicted it 2 years before it was discovered in Germany. He predicted all of the properties of it, and he predicted the approximate weight of it. It was discovered 2 years later, and by that time, people started giving Mendeleev some credit. They realized, okay, so you saw a dream and you predicted the future, but you're right. So they finally agreed and said, wow. Yeah, one time I had a dream and I predicted the future. He predicted all sorts of elements that were going to be discovered. And we're discovering elements years after he passed away. Mendeleev's table became the basis for the periodic table. So what we see today is actually developed straight off of what Mendeleev did. Every single column is based on periodic properties, based on the groups. All of these have similar bonding tendencies based on the similar properties of the elements. Yes?
You know how some people have problems with the history and the theory for type of stuff beyond the AP text, like questions about Mendeleev and stuff?
They do like to put some history in there. They usually don't do free response questions on it. No essay. But they like the free response stuff. They love to put, in general, on many scientific tests, they like to put the scientific method type ideas into it. So this is one of the things that people tend to have trouble with. This here is a picture of Mendeleev's early periodic table. This one was published in 1872. So a few years after his dream. This was the first one that people kind of laughed at and said, wait a minute, there's a hole there. There's nothing there. There's a question mark here? What's up with that? Like, you don't know what goes there? You don't have the answer? It must be wrong. But from this relationship of the data, he was able to predict things that went into these spaces here. And from those predictions was able to predict elements that hadn't been discovered yet, elements that hadn't been found, and even elements that hadn't been made yet. Now, after Mendeleev came along J.J. Thomson. To the electron, may it never be of any use. Mr. J.J. Thomson. He was the one that discovered the electron. Unfortunate quote, but that's life. Joseph John Thomson, J.J. Thomson. He was researching in England. He experimented with cathode rays. Cathode rays were the precursors to the television, so you can thank him for making televisions. He didn't make them, but he did some experiments with cathode rays. A cathode ray here, tube, has a slit in which the electrons can visibly be seen by the fluorescent background strip. These cathode rays were originally not known what they were. When you place a magnet up to them, okay, they go towards the positive side of the magnet and away from the negative side of the magnet. If they go towards the positive, what charge must these cathode rays have? Negative charge. You also saw that they cause a shadow, and so these particles must be particles and not just energy, and two, they must have a negative charge. So he discovered particles with negative charge. He showed that they could be deflected by electric and magnetic fields, both of them. And this allowed him to discover the electron. So if you had here a negative magnetic field here, a positive electric field here, okay, went towards the positive. Here when you have a magnetic field, the electrons or the negatively charged particles went towards that magnetic field. He was able to compare the differences in deflection, revealed that cathode rays have mass and negative charge. Mass and negative charge. Thomson called these particles corpuscles. So instead of how many electrons does the element have, you can just say how many corpuscles does it have. But we've changed the name since. He was able to determine the charge to mass ratio of 1.755820 times 10 to the 8 coulomb per gram. He was able to scientifically gather this information that not only does it have mass and charge, but there is a ratio that is always true for these corpuscles. They were later called electrons, since people probably didn't like the word corpuscle. Or many other reasons. Electricity probably related to that. Thomson believed these electrons were emerging from gaseous atoms in the cathode ray tube. So he believed that there was a gas in here, and that was emitting these electrons in the tube. The discovery of the electron proved that atoms are divisible. They're made up of smaller things. In 1903, he proposed the plum pudding model. Now, how many of you have ever had plum pudding? Raise your hand. All right. So, plum pudding is really strange. I mean, not strange. It tastes pretty good if you ever get a chance to eat it. But I did the same thing. Someone said plum pudding model. I said, I was thinking like a long time ago, I used to eat pudding that Bill Cosby would advertise. And it was like this Jell-O pudding, like just those pudding snacks, you know? And I thought you would stick some plums in there. And you'd like cut them up and stick plums in there. I'm like, that would be nasty. I'm like, it's ridiculous. And when my chemistry teacher told me plum pudding, I was like, okay, weirdo, scientist, whatever. But the reality of it was plum pudding was a very popular dessert in England. That's like saying this, instead of being a plum pudding model, how many of you have ever eaten chocolate chip cookies? Alright? If you don't like chocolate chip, you can do raisin, oatmeal, but that's... whatever, you can go that way. But chocolate chip cookies are something I love to death. I can actually smell the chocolate chip cookies right now in my mind. It's so awesome. Right out of the oven, warm. Put some ice cream on it, make a bazooki. Oh. Anyways, chocolate chip cookie. Now, imagine that chocolate chip cookie, and you take it three-dimensional. You make it into cookie dough ball, but you make it all cookie. Three-dimensional cookie. Inside the cookie, there's dough and there's chocolate chips. This is like the plum pudding model. There's dough and chocolate chips. The chocolate chips and the dough both stand for something different. So, here's the dough. The dough is this pink stuff. This represents a sphere of positive charge. So all the dough is a positively charged sphere. The electrons are the chocolate chip cookies. Now you're looking at it going, wait a minute, is this really 3D? It looks 2D to me. Yeah, you could imagine it to be 3D if you can. It's a sphere, not a flat cookie. But chocolate chip cookie model works great for me. It's easy to remember. It was in 1903. He said the atom was like plum pudding, chocolate chip cookie. A bunch of positive stuff with removable electrons. So you can remove the chocolate chips from it. Yeah, why would you? I don't know. But, all right, there's a debate. Now, electrons. Okay, you had a positively charged pudding And what he thought was, how do you form a positive ion? You take one of these out. And if you take a bunch of these electrons out, you can have conduction of electricity. So his model actually explained more of what could happen and more of the theory of electricity, which they were trying to determine at this time. So that's why they were called the electrons when they got removed. So 1803 was Dalton. 460 BC was Democritus. We don't even have him on there. He's like, woo, all the way bottom. 1903, 100 years later, is when Thompson found the plum pudding model. 100 years later. And in between, we got a periodic table out of the deal. All right? What happened next? Robert Milkins said, the fact that science walks forward on 2 feet, namely theory and experiment, sometimes it is 1 foot that is put forward first, sometimes the other. But continuous progress is only made by the use of both, by theorizing and then testing, or by finding new relations in the process of experimenting, and then bringing the theoretical foot up and pushing it on beyond, and so on in unending alterations. You keep going. Sometimes you find one thing before the other. That's okay. Robert Milkins, 1868 to 1953, from the US of A. He did an experiment with an oil drop. His experiment is one of the coolest ones, at least one of the coolest ones, I think. What he did was he found out that if he could get an electron with a negatively charged, a cathode ray, a corpuscle, he could control that with a magnetic field. So what he decided was, I'm going to take some oil, some very, very small pieces of oil, and I'm going to charge them. I'm going to add an electric charge to them. And then I'm going to have them fall like they normally would. And then if I apply a magnetic field just right, I'm going to have that drop of oil hover in midair. Yeah, I'm like, dude, that's some awesome things. I don't know if he thought of the idea first, or if he did the experiment first, right? We don't know. He says he does it both ways. Who knows? What comes first? What comes second? I don't know. But the cool thing was he was hovering oil in midair. I mean, that by itself is cool. But then he decided to take it a step further. He determined the charge on an electron by that experiment, by charging up these drops of oil and determining how they fell and how much magnetic field or electrical field he would have to add. This charge he determined was a very small number, 1.6 times 10 to the negative 19 coulombs, and this led to the mass of an electron. So he was able to show the actual mass, not just the charge to mass ratio, but the actual mass of a single electron from his experiment. The mass they determined was that a mass of an electron is about 9.1 times 10 to the negative 29th grams. That's why so far we've been saying the mass of an electron is 0. Proton is 1, neutron is 1. Because it is very, very small. It's about 1,800 times smaller than a proton. How did he do this? He took a little bit of oil and sent it through an atomizer. Now, an atomizer doesn't actually make it atoms of oil. It just shoots it out into very small pieces. Then they went through a positively charged plate. A small amount went through in a single line, and he added ionizing radiation to them. He also had a light source so he could see these droplets. And he had a negatively charged plate here and a positively charged plate. Since the electrons were negatively charged here, they were attracted to the positively charged plate. So he could cause them to go up or go down, depending on how much positive charge he had on the positive plate. He could also adjust the negative plate as well, and was able to do that to control where the electron was. Where the drop of oil was, because the drop of oil had electrons on it. He was able to view this through a microscope, because again, these were small, but they were not atom size. In his experiments, he did these experiments from 1908 to 1917. So as you can see in this animation, the droplets, some of them fell through the hole. He used an X-ray to ionize the gas molecules. Oh, hold on, it's going to be loud.
Now carrying a negative charge. The negatively charged oil droplets
So all you had to do was find out the ratios, first of all, to get the charge. Then once you have the charge, can you do this calculation too? Yeah, pretty easy. Just a little dimensional analysis, no problem there. Okay, the relationship, although the measurements were the difficult part that he had to spend a while getting these measurements just right. Yeah?
You said that previous slide was 10 to the negative 29.
10 to the negative 29th. I'd have to look and see which one of those is correct. Yeah, I think there might have been a typo on the original slide, but I don't think this looks right. I have to check both of them. Yeah, because you got 19th and 1.76 times 10 to the 8th. I'd have to check both of those because they're from two different sources. You think it's 28th? Yeah. Okay. Notes say 28? Okay. So that I might have changed it as I was editing something.
Old notes.
I got old notes?
Yeah.
Yeah, I'll have to fix that.
Like the first one.
Now, the next person that came along, his name was Ernest. What was his name? Ernest. Now, Ernest Rutherford did an experiment in which he said it was quite the most incredible event that has ever happened to me in my life. That's pretty exciting. I mean, really. I don't know what else went on in his life, but that's pretty exciting. Okay? Now, how he described it, it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This is the experiment of Ernest Rutherford, the most surprising event of his life. Rutherford's Experiment. Ernest Rutherford was a contemporary of J.J. Thomson. He actually wanted to find out if Thomson's plum pudding model was correct. So what he did was he took some radioactive material that he'd been working with, and he fired that radioactive material at a very small piece of gold foil. When he did this, he said it was like shooting a shell, 15-inch shell, at a piece of tissue paper. The particles he was shooting had such an incredible amount of mass and such an incredible velocity that it was like shooting a rifle at tissue paper. And somehow the bullet came back and hit him in the head. That's the analogy he was using. It's like it bounced back. So, in that experiment, he discovered that most of the mass of the atom is concentrated in the tiny center, or the nucleus of the atom. The nucleus is positively charged. He used uranium to produce positive alpha particles. Uranium is radioactive. It produces an alpha particle spontaneously. He aimed those alpha particles at gold foil by drilling a hole in a lead block. So he fired them through lead, these positive alpha particles, towards gold foil. Since the mass is evenly distributed in gold atoms, alpha particles should go straight through, was his theory. Just like they should go straight through the cookie dough model. So this here is the source of radiation, the lead block. He had a detector screen that went all the way around. He fired it towards the gold foil and he expected most of them to go through. His observations were almost 100% accurate. He fired it thousands of times, and most of the time it went through. But every once in a while he got one that went off to the side. He did this experiment many times because he didn't believe it. He did not believe that it was possible that one of these particles could bounce back in this direction or back towards the detector, towards the source. This seemed impossible to him. Plus, if he agreed with his evidence, he proved his friend wrong. Okay? That really sucks. You're like, I'm going to prove you right. Oh, now I'm going to prove you wrong. I get all the credit. I mean, it sounds really selfish, but he was trying to prove his friend right. Yeah? He was shooting what are called alpha particles. They are radioactive particles that are spontaneously emitted from a uranium atom. And these have a incredibly high velocity, and they're like a helium nucleus. So nucleus of a helium atom, they have a mass of 4 and 2 protons in them. And the nuclei, these particles, he expected them to go straight through because he thought the gold foil was not going to stop them at the velocity they were going. He thought they would just be able to pass through without a problem because they were so massive and the gold foil had mass so spread out. It was the thinnest piece of foil he could make. So it was like super, super thin, like he wanted to make it a few atoms thick if possible. He was able to do that pretty well with the gold foil. So that's why he called it like tissue paper, and then this was like a big missile or a big a bullet traveling in that direction. From this, he thought they would all go through like this. So he thought that all of them would go through, straight through. Okay, if these were positively charged, and you shoot them through a positive medium, if they have enough velocity, they're going to go straight through. The negative charges of the electrons might cause them to turn or deviate just a little bit, but not much, because they have too much speed, right? So they have so much velocity, they're not going to be pulled back at all. His actual results showed that some of them bounced right back at him, and some of them deflected. What he found was the discovery of a nucleus. And he learned that the nucleus of an atom has PMS. Has what? PMS. He learned that the nucleus of the atom was positively charged because he had a positive particle going towards it. In order for it to deflect the positive particle, it had to be positively charged in order to electrostatically repel it or deflect it. It also had to be incredibly massive. The M stands for massive. Had to have enough mass that the mass times velocity momentum of the particle would not cause it to just go like this. Whoop, billiard ball. Had to stay in place somehow. Okay? So the mass of the nucleus had to be incredibly high. And the other thing that had to happen is it had to be incredibly small. PMS, positive, massive, and small. How can it be massive and small? It would have an incredible density. And the density was so great that it could cause a particle moving at a high velocity with a positive charge to bounce backwards. And his actual result allowed him to discover that the nucleus of the atom is composed of something positive, massive, and small. This picture here, I do apologize, is absolutely wrong. Rutherford was not able to prove the existence of a neutron. He just thought it was a positive nucleus. He had no idea that neutrons were present there. It wasn't until 1928 that Chadwick found and got evidence and got credit for discovering the neutron.
How did he find a neutron if he was using it?
Ah, that's a great question. You look up Chadwick's experiment. I don't think I have it on this slide. We can go into that later if you want, how he discovered it. He does not get a lot of credit in atomic history, unfortunately. But here's a picture of what's happening at Rutherfords Experiment, if this works. If I get this to work. All right, here's a picture of Rutherford's experiment. So what did it look like? What was he doing? So here was Thomson's model. He was trying to prove it. This is what Rutherford actually expected to have happen. So this is what Rutherford actually expected, most of them to go through. And the truth of the matter, this fact that most of them actually did go through showed that the atom was mostly empty space. Most of them went through, but occasionally you got one that did not. Now, the percentage of the ones that went through is 99.95%. So this is Rutherford's new model of what's called the nuclear atom. So that is Rutherfords Experiment. This here is another widget that shows what happens when particles are shot out at the nucleus. The nucleus is positively charged. So even though the nucleus has a small mass, it's able to deflect a large number of positively charged particles. So now we're up to 1911. We've got Dalton, we got Thomson, we got Rutherford. A nucleus contains nearly all the mass and the positive charge. And this is a baby. I don't know. Now the cool thing is, even though atoms are not visible, you cannot see them with your eye. Okay? These scientists in March 6, 1981 developed what's called a scanning tunneling microscopy. A scanning tunneling microscope. This allowed Gerd and Henrik to see the first atoms. Okay? Now, this was a visualization technique. This is not actually how the atoms view, apparently, or are viewed, but you can see where their location is. And from the individual atoms here, here is the word atom written with atoms in Japanese. Hey, that's what I saw. It said Japanese to me, and I don't know Japanese or Chinese, so you guys can just debate that all you want. That's loud. So even though it's impossible to see atoms, there are ways of visualizing where they're located. And moving individual atoms is something that a material science engineer does. They actually can physically move the atoms by using a scanning tunneling microscope as well as using some other electronic forces. They can move individual atoms to different places to create materials with different properties. And this is one of the uses of being able to actually see those individual atoms, although again it's much more difficult to quote-unquote see them using this device. But it does allow us to give us a better visual of what's happening in the atom. So, a couple things for you to know. First of all, lab number 8, that is going to be happening tomorrow. Our reaction quiz has been moved back to Thursday from Wednesday. What's the reaction quiz on? Let me see if I can show you what it's on.